Okay, so thanks everyone for coming. Today, as you probably know, we've got Andreas Schmittner. For those of you who don't know him, he's a professor here in the CEOAS department. And so with that, I'll let him take over. Go ahead, Andreas.
Thank you, Ken. Thanks a lot, everybody, for tuning in. I've just put together some slides pretty quickly. So this is not a polished talk or so, but I just wanted to share some recent results regarding the ocean at the last glacial maximum, which has been a focus for our group for the last years or so. Juan Muglia, who is also on the call, has been contributing a lot of the work. And then another contributor is Sophie Wilms, who has been doing kind of the tidal mixing work that I will present. So the talk will have these two parts. In the first part, I will talk about these tidal mixing results. And in the second part, we'll discuss some new results from Juan about how can we reconstruct AMOC strength versus depth. So geometry versus dynamics, if you will. So, okay, let me just jump right into the first part, the tidal mixing part. And this has been published partly in this paper here that came out last year. And some of you may remember Sophie Wilms, who has been here for a couple of months or for some months, but is now back in Bangor. And this paper that we published in Paleoceanography that was looking at essentially the physical effects, the physical response of the models to changes in tidal mixing in the last glacial maximum. And then more recently, she has been looking into the biogeochemistry and isotopes and comparing with sediment data. And that is most of the part that I will present here. So I will kind of skip over most of this part because I think, or this published paper part, because that has been already presented before. And many of you may have seen Sophie talk about this when she was here. But just as a kind of brief introduction about the method, what we're doing here is we use tide models and climate models and combine those results. So for the tide model, we use OTIS, the Oregon State Tidal Inversion software developed by Gary Egbert. And we simulate here the four main tidal constituents, M2, S2, O1, and K1. And then we've done, with this model, we've done simulations of the last glacial maximum at different, and we have tested different things, the sensitivity to different parameters, if you will, because initially the idea was we wanted to find out why there were two published papers that came to completely different conclusions. One said there were no, so the changes in the tides were not important, and there were no large changes in tidal mixing at the LGM, and another paper said there were large changes. So in order to figure out why those discrepant results were published, we did a large number of sensitivity tests, I should say. Sophie did those. And she ran the tide model at different resolutions, up to 1/12 of a degree. She used different internal tide drag parameterizations and different LGM bathymetries. And to give away here the main results already, because I won't be talking about it, it turns out that the results are not very sensitive to the different resolutions or to the different tide drag, internal tide parameterizations. However, they are different. They are sensitive to the different LGM bathymetries. We've used ICE 5G and ICE 6G reconstructions. And what they depend on very strongly is the ice extent. So the land ice extent that then changes the geometry of the ocean basins. And that affects the tides strongly. So then what we do with these tide model simulations, we use them as input into the climate model, the University of Victoria, its intermediate complexity climate model with a simple atmosphere, but a reasonably good coarse resolution ocean. We do have standard tidal mixing parameterization in there. And what is unique about the model is that we also have isotopes and the full carbon cycle and biogeochemistry in there. So that's this MOBI model here that we've developed here. And that includes the isotopes that we can actually compare with sediment data from the glacial ocean, like radiocarbon and C13. Now, what we do with this model is, in addition to these different tides from the LGM, we also vary buoyancy fluxes in the southern ocean, which gives us different overturning circulations, just as sensitivity tests. And I will show those results and talk a little bit more about how we do this in another slide. And in terms of LGM boundary conditions in the model, those are pretty standard. So we put ice sheets over North America and Northern Europe. We lower our greenhouse gas concentrations, and then we change the orbit as well. And so here are some of the results that I just want to review from the published paper, from the Wilms et al. 2019 paper. And on the left, it shows the global mean or global integrated tidal energy dissipation from all of those 4 tidal constituents for depths below 500 meters. And here the black symbols are the present day simulations, or present day tides. And the blue is the ICE 5G reconstructions, and the red is the ICE 6G reconstruction. And then there's another experiment, the green one, where she has just lowered sea level by a constant value of 120 meters. And so what you can see is, and then also here, these 2 columns are different internal tide drag parameterizations. This one here on the left is the Zern and Egbert parameterization. And then on the right, we have Jane and St. Laurent. So as you can see, for the present day, both of these internal tide drag parameterizations give a number close to 1 terawatt energy dissipation from tides. But if we go to the LGM bathymetries here in red, the ICE 6G, we get about a doubling of the tidal energy dissipation, so about 2 terawatts. And if we go to the ICE 5G, even more, 3 or even a little bit more than 3 terawatts of tidal energy dissipation. So that's really a big effect. But not only it's a big effect, it's also very sensitive on which precise ice reconstruction you're using, as you can see here between the red and blue symbols. And on the right-hand side, is those are showing maps of the changes in tidal energy dissipation. So those are both for the Zern and Egbert parameterization, but the upper one is the ICE 5G bathymetry reconstruction, and the lower one, the ICE 6G. And what you can see in both is that the increase in the tidal energy dissipation is largest in the Atlantic, here along the Mid-Atlantic Ridge, in the North Atlantic, also in the South Atlantic, and not so much in the Pacific. There's a little bit in the Indian Ocean in the ICE 5G, but not so much in the ICE 6G. And in generally, the ICE 6G has not as large of an increase in tidal energy dissipation compared with the ICE 5G reconstruction, and which is partly a response to the changes in boundary conditions. If you look closely here at the Weddell Sea, you can see that the ICE 5G has not as much extent of the ice, the land ice extending not as far out onto the shelf in the ICE 5G as in the ICE 6G simulation. And this influences the tides, particularly in the South Atlantic, and leads to these large differences between these 2 reconstructions that we see there. So that's kind of the basic results from that published paper that you may already know. And then here are some of the details of the tidal mixing parameterization that we use in the climate model. So the vertical or the diapycnal diffusivity, KV, is essentially calculated using this equation here. So it's a background value KBG, which is fixed at this number here, plus gamma times epsilon. Gamma is the mixing efficiency, epsilon is the tidal energy dissipation rate that comes from the tide model, divided by n squared. And the tidal energy dissipation rate is calculated here by the sum over all the tidal constituents, TC, and then we also use a subgrid scale parameterization, so we sum up over all the depth of the subgrid scale, depending on the high resolution bathymetry. And then this D here, this is the map that comes from the high resolution tide model. And this Q is the dissipation efficiency. That's the fraction of locally dissipated energy, which depends on the tidal constituent. But for most tidal constituents, it is, or the most important ones, it is 1/3. And what that means is that only 1/3 of the energy dissipated is locally dissipated, and 2/3 propagates away as internal waves and dissipates elsewhere. So what we're dealing here is only that locally dissipated energy, and we're ignoring changes in the remote, in the propagation and the remote dissipation of energy. So that's an important point to keep in mind when we interpret the results. Okay, this F function here is an exponential decay above the seafloor. So that's the vertical, that determines the vertical structure of that energy dissipation rate. Okay, so, and feel free to interrupt me if I'm going too fast here, but I just wanted to get the technical details here more or less wrapped up pretty quickly. So here are the main results from the climate model simulations, and this matrix, you can see the three columns that represent present day tides on the left, and then the ice 6G tides in the center, and the ice 5G tides on the right hand side. And then the different rows, they are different moisture diffusivity in the southern hemisphere. So we start with a standard model at the bottom, and then when we decrease the moisture diffusion in the southern hemisphere, that leads to less moisture diffusion towards the high latitudes, less precipitation close to Antarctica, which leads to saltier Antarctic bottom water, and so more intense Antarctic bottom water, and also shallower and weaker AMOC. As you can see, when we go from the bottom here towards the top, the AMOC gets shallower and weaker. And this the top one here for present day tides is the extreme case where the AMOC is collapsed completely. Okay, and then if we use the same setup but for LGM tides with the more intense tidal mixing in the center and on the right hand side, you can see that the AMOC is stronger compared with the present day tide input. Okay, so those are the circulation stream functions, and I have this is kind of illustrated a little bit more also in these scatter plots that I'm showing you now. So perhaps let's start with the figure, with the panel here on the lower right, which shows average diffusivities in the Atlantic between 30 south and 30 north. And the reference, the pre-industrial control simulation is the gray line here that shows the diffusivities in that control simulation. And then all the black lines are the ones with present day tides, so LGM simulations, but using present day tides. And then the red ones use the ice 6G tides, and then the blue ones use the ice 5G tides. And if you compare just all the black thin lines with all the red thin lines, you can see that the diffusivities are increased in the LGM tide simulations, and they're even more increased if you use the IS5G, which are the blue lines. Now, the differences between the different blue lines here, those are caused by differences in stratification. And you can see this if I go back here to the formula. So the diffusivity depends not only here on the energy dissipation rate epsilon, but also on the stratification n squared down here, right? So as the stratification changes, you get some modification of the diffusivities despite a constant energy dissipation rates. And that is mostly important for these cases here with strong and deep overturning. For example, this dashed dotted blue line, which has a very strong and deep overturning that is probably unrealistic for the LGM, as we'll see in a moment. In this case, the diffusivities are much larger than in the shallower and the weaker overturning cases. For example, here the solid lines.
Excuse me, Andrea.
Yes, Ricardo?
Ricardo, please.
Yes.
Why there is an increase in vertical diffusivity between intermediate depths between 1,000 and 3,000 meters in the ice simulation?
Yes, are you asking why there is an increase in diffusivities there?
Yeah.
I'm not exactly sure, but if we go back to the figure here in the map, so you can see a lot of the increase here is along the Mid-Atlantic Ridge, and maybe that extends that high up in the water column. And we have been averaging between
Andreas,
30 south.
isn't that nominal ridge height about 2,500 meters?
2,500 meters. Let's see if. So if the ridge height is at 2,500 meters, you could get some of that increase here from that. So I'm not sure exactly where that. It may also be from the boundaries here, maybe here from the Caribbean. So I'm not exactly sure where that comes from, but it should be. It should be here on the map. So wherever those shallower increases are.
Andreas, while you're on this question, what is the vertical decay scale in that f of z prime function?
Yeah, that is 500 meters.
Okay, thanks.
So you could get from 25 to 2,000 meters or so with that. Yeah, good question. Maybe we should look a little bit more into that. Thanks, Ricardo. Okay, so the bottom line is that the diffusivities are increased due to that increased tidal mixing, and then that increases the overturning rates, and both AMOC and also Antarctic bottom water are increased, and that you can see here in this upper left figure that shows on the horizontal the AMOC strength, and on the vertical the Antarctic bottom water strength. And the black dots are the simulations with present day tides, red dots IS6G tides, blue dots IS5G tides. And for reference, the pre-industrial control is this cross. So, if you just look at the black dots here and then relative at the red and the blue, you can see that both Antarctic bottom water and AMOC are both increased. So you are moving essentially towards the left and downward from the present day tides. Okay, so that kind of seems to make sense, higher diffusivities, increased overturning rates. And then here on the upper right, this graph, I just want to introduce that one because it turns out to be important for the part 2 discussion. It shows the AMOC strength in the horizontal and then the AMOC depth in the vertical. So what you can see is that essentially all of these LGM simulations, they plot more or less on a line and indicating that in all of these simulations, the AMOC strength is highly correlated with AMOC depth. So models that have a stronger AMOC also have a deeper AMOC, and models that have a weaker AMOC also have a shallower AMOC. And as we will see,
sorry, Andres, are those numbers just the location and the amplitude of the maximum of your overturning stream function?
The AMOC strength is at 25 north, and the AMOC depth is averaged over 30 north to 30 south. So it's the depth of the zero stream function contour line.
Oh, okay.
Okay, and then let's just talk about this lower left plot for a bit, which shows again the AMOC depth on the horizontal axis. But now the diapycnal diffusivity on the vertical, the diapycnal diffusivity, I should say, averaged on that zero stream function isoline. So that essentially that represents the separation between Antarctic bottom water and North Atlantic deep water. And previous papers, like there's a paper from Ferrari, who have suggested that due to the shoaling of the AMOC and the LGM, you essentially move away from the bottom and you move away from high rates of mixing. And that then leads to more isolation between Antarctic bottom water and North Atlantic deep water, just by that, through that vertical shift. And that could, have implications for increased carbon storage in the LGM, for example. But what we are showing here is that although that, that shift is true, if you shift from deeper on the left to shallower, if you just look at the black dots for now, you do indeed decrease the diffusivity on that interface, right? So you go to lower values here. But if we then use the increased tidal energy dissipation, if we incorporate that as well, that can compensate for it, for example, the red lines, or it can even increase the mixing at the interface despite shoaling. So for example, if you go from this dot here at 3,000 meters with present day tidal mixing to the blue line, to the blue dot with at 2,600 meters. So this has been shoaled, but due to the increased tidal mixing, tidal energy dissipation, you still get an increase in diffusivity at the interface. So that is something that we would suggest that those other authors should be considering in the future.
Andreas, can I interrupt you?
Yeah. Sure.
Just back on that slide, there was something I didn't understand on the upper left. Yes. Your AABW strength on the upper left panel is they're negative. Is that just a sign convention, or is it an anomaly?
Yeah, well, so more negative would indicate a stronger Antarctic bottom water flow rate.
Okay.
Yeah, so that's
because it's you're using a different sign for that bottom.
Right. Yeah, it's counterintuitive maybe to put it that way, but if you look at these stream functions, the Antarctic bottom water stream function is always negative. It's
so it's just the way you calculate it from top.
Yeah. Right.
Yeah. Okay. No, I get it. But and this is also calculated at, what did you say, 20 degrees north or 30 degrees north or something? Or
Antarctic bottom water strength, I think that is at 30 south.
30 south, and AMOC is then in
25 north.
Okay, so it's at different places.
Right.
And so what it's saying is that when AMOC is stronger to the right, AABW is weaker up. Is that right? The trading.
Right, right. So for those very strong cases, or strong AMOC cases, it essentially pushes out Antarctic bottom water, and you have weaker Antarctic bottom water, right?
Okay.
And
and
the
then
weaker AMOC cases.
And then the different dots within a color. So that's your different simulation where you're torquing the buoyancy flux in the Antarctic. Is that right?
Right, right. All the different dots are for one color are with different buoyancy fluxes in the Antarctic, right?
And presumably high buoyancy flux means high ABW?
Mm-hmm. Right. Well, no, low buoyancy flux.
Low.
Yeah.
Okay.
Right. Mm-hmm.
So high buoyancy
So
flux trends up to the right. Okay.
Trends up to the right. Right. Exactly.
Okay.
Mm-hmm.
Yeah. It was just, and then the X is off the trend of all the others, and that's an observation or a model result.
That's a pre-industrial control model. Yeah, that's the model. But the model is pretty, I mean, at least for the AMOC strength, that is in pretty good agreement with modern observations. So a modern observation at 25 north are around 17 Sverdrup. So it's pretty spot on here, that model. Okay. I'm not sure about the Antarctic bottom water, but I think it's also more or less in agreement with data.
But is it saying that your buoyancy flux is more powerful than the difference between the tides?
I guess you could say that, you know, if you look at the range here from different buoyancy fluxes, it has a larger impact than the different tides. So the different tides have, you know, this impact here, and the different buoyancy fluxes, you know, you go along that line. Of course, it depends on the number you're using, but
yeah,
as
sure.
a general,
but then
you can get larger effects from buoyancy fluxes than from tides.
And you know, because you're imposing that buoyancy flux, what is that simulating? You know, you're making it do that, obviously, but what do you?
Yeah.
What's the physics?
Well, I guess I can talk about this. I mean, our primary objective is to create different circulation strengths.
Yes.
And that is just a method in the model to do this. But in terms of physical mechanisms in the real world, you can think of that. You know, whatever controls atmospheric moisture transport in the mid latitude southern hemisphere, the winds, the eddies there. You can also think of processes that are currently neglected in climate models, which is ice-ocean interactions, for example. So if you think about the glacial ocean, it was colder, right? So currently there's a lot of basal melting of ice shelves, and many of the icebergs, they melt close to Antarctica. In a glacial colder ocean, you would expect less basal melting, so less freshwater input from that, and then more freshwater input from traveling icebergs further north, melting there. And so none of those processes are included currently in climate models, and neither in the UBIC model. And perhaps, you know, you can think of that kind of affecting buoyancy fluxes, and we are mimicking that perhaps in a way by changing the diffusivity in the atmospheric moisture flux.
Got it. Okay.
So those are some of the mechanisms that you could think of.
But the trajectory that the ocean would move from the X, the modern pre-industrial, to one of those dots in the glacial, depending on whatever the buoyancy flux is for whatever physical process is causing that in the glacial. Is that right? So in other words, you could move to the left on the diagram if those buoyancy fluxes are right, or you move up on the diagram from the pre-industrial to the glacial to hit some place in that distribution in your dots. Like starting from the X, you could either move to the left or up, or anything in between, depending on what's going on with the Antarctic buoyancy flux.
Yeah,
whatever else.
I mean,
Is that right?
right. I mean, the AMOC is not only controlled by Southern Ocean buoyancy flux, right? That's just one factor that affects it. And for example, one difference between the pre-industrial simulation here and all the LGM simulations is the winds. And as Juan Muglia in his paper a few years ago, is that the wind effects in the North Atlantic due to the ice sheet presence there in the LGM. It accelerates the wind-driven gyre and therefore salinity transport and hence the AMOC. So that's another effect that leads to that causes a stronger AMOC in the LGM compared with present day. And then there's various other processes like basin-wide E-P in the Atlantic, and you could think of many other processes like Bering Strait closure and so on.
Right. Okay.
Okay, let's see. So I was going to present some of the comparison to the LGM data, the sediment data. And this here shows the radiocarbon. So now, the matrix is essentially the same that I showed earlier for the overturning circulations, and now the colors is radiocarbon age. And the reddish, orange, red colors are older radiocarbon ages, and the bluer are younger ages. And what you can see in general is that the North Atlantic deep water is relatively young. It comes from the surface, and Antarctic bottom water is relatively old. It's older than North Atlantic deep water. And for those simulations that have a weak AMOC, like here in the upper right corner, that's the extreme case, the collapsed AMOC that has very old deep waters in the North Atlantic. But also those shallow, weak AMOCs, they have deep, old deep water in the North Atlantic. And the strong and deep AMOCs, they have young water filling the entire Atlantic, essentially, down here in the lower right. And the dots here are the sediment data, and you can see already that the deep and strong AMOC simulations do not fit very well the data. And what we find is that those weak and shallow AMOC simulations here in this area, they fit the data better. And I'm going to show you some more RMS errors and so on in a few slides. But just here, the other proxy that we're using, the C13, so that's the stable carbon isotopes. And you can see there is much more data. So here we have 400 sites, mostly in the Atlantic, whereas for radiocarbon, we have only around 120 sites, and they are quite evenly distributed between the Pacific and the Atlantic. For the C13, higher values are in purple, and lower values are in brown. And you can see also that now a deep and strong AMOC has these high C13 values in the North Atlantic, because those are coming from the surface. Surface C13 is high, and North Atlantic deep water advects those into the interior. So the deep and strong AMOC simulations have these high values in the deep North Atlantic, whereas the shallow and weak simulations, they have these low values in the deep North Atlantic. So these patterns are not dissimilar, just anti-correlated to the radiocarbon patterns that we've seen before. And again, we would find those weak shallow AMOCs fitting best. And that is shown here in this graph in the top, and on the left, radiocarbon age. The global data is shown on the very left panel, and then the Atlantic only in the right panel. And yeah, let's look at that one first, at the global one first here. AMOC strength is as a horizontal axis, and then the root mean squared error of all the data in radiocarbon years on the vertical axis. And now you can see that the black and red and blue dots, they almost fall all onto one line, onto a curve that has a minimum here around 9 Sverdrups. So this is what we would, call the best estimate then for the LGM AMOC strength. It's around 9 Sverdrup, and that is compared to 17 Sverdrup in the modern ocean, right? So much weaker. I was kind of surprised that all of these dots fall essentially on one line here. But if you look at the Atlantic only, you can see some separation between the different tidal mixing runs. And now the black dots with modern present day tidal mixing, they have slightly higher RMS errors than the ones with higher mixing. And the ones with the highest mixing, the blue ones, the ICE 5G reconstructions, has the lowest errors in the Atlantic. And that is also the case for the C13 if we look at these lower plots here. So for C13, also slightly better agreement with the higher mixing simulations, although it's relatively subtle compared to the differences from the buoyancy forcing here, so which are the differences between one colored dots. On the right-hand side, we see basin-wide averages of those two tracers, so radiocarbon on the left and C13 on the right. And so the data, the sediment data, are shown individually as the symbols with the error bars, and then the average sediment data, horizontal average, is the white line, and then the gray shading is the one sigma error bar. And then all of these different lines are the different simulations. And you can all already see the ones with a very deep and strong AMOC, they have a very horizontal profile that doesn't fit the data very well. But also this simulation here, the black with the crosses, is the collapsed simulation that doesn't fit the data either. And so the ones that fit the data best are the ones with something like 9 Sverdrup or so of overturning. And if we just isolate the three ones to look at the differences between the tides. So now I've selected three simulations here that all have around 9 Sverdrup of overturning, but they only differ in the different tides. So the black one is again the present day tides, the red one, the ICE 6G, and the blue solid line here, the ICE 5G. And if you compare those three with the white line, you can see that the blue solid line, so the ones with the largest mixing, most closely approximates the white line. Whereas, for example, the black dashed line here, which is the present day tides, it has a larger gradient here at mid depth at around 3 kilometers, a larger vertical gradient than the data. So, even though those differences are quite subtle, there seems to be perhaps a possibility to constrain some of the models with the data. And the same is also true here for the C13 data. The blue solid one has the smallest gradients at intermediate depth and therefore fits the data better there compared with the simulations with less mixing. So, although I would say this, the data do not have very strong constraints here on the mixing, but there seems to be some signal and seems to be some slightly better agreement with those higher mixing simulations. Okay, how am I doing with time? that was part one, essentially.
I think if, maybe 15 minutes, Andreas.
15 minutes, okay, I'll try to speed up a little bit.
Okay.
But we've got all the introductions already, so hopefully part two will go faster. So what I would conclude here now from part one is that, first of all, increased tidal mixing in the LGM in all of our tide model simulations is a robust result. Doesn't depend on tidal parameterization, internal wave drag parameterizations, on resolution very much. But it does depend strongly on that reconstructed bathymetry, so on the land ice extent especially. Then these increased diffusivities resulting from the increased tidal mixing, tidal energy dissipation, lead to increased AMOC and increased Antarctic bottom water flow rates. And the AMOC, well, the AMOC strongly affects those isotopes. So the AMOC structure has a larger effect on the isotopes than the tidal mixing, even though there seems to be some subtle differences in the simulated isotope patterns that seems to suggest support for higher mixing, for those high mixing simulations. But another important point I wanted to make here is this one, because if you remember at the beginning, I mentioned that we're only looking at that 1/3 of the tidal energy that is dissipated locally. So we're ignoring any changes in the remotely propagated energy that is remotely dissipated. And that effect would, of course, you would expect it to increase essentially the effect of the larger tides on the LGM circulation. So you would expect it to increase diffusivities elsewhere, which would also lead to an additional strengthening of mixing and of the overturning, presumably. So that is something that I would like to pursue a little bit more further by including a parameterization of the propagation of tidal energy dissipation, the energy and the remote dissipation. Okay, so that was part one. Now we'll come to Juan's results regarding AMOC depth versus strength. And just as an introduction, as we've seen in these previous experiments, AMOC strength and depth were correlated. So, whenever we found a good fit with the data and the LGM data, the sediment data, we were not sure, was that due to the AMOC strength or the AMOC depth? So we could not really separate those. And now Juan has done some additional simulations that where we can look at these two properties separately. And the way he has done this, he has used those southern hemisphere moisture diffusivity runs that I showed you already in Sophie's runs, and then he has combined them with North Atlantic freshwater fluxes. And the result of that is that you essentially it's illustrated here in this graph that shows the AMOC strength on the horizontal and then the AMOC depth in the vertical. And the previous simulations are those here in the black, surrounded by the black line. So they are highly correlated. So where AMOC, as AMOC gets stronger, it also gets deeper. And now adding these additional simulations with North Atlantic freshwater, essentially negative freshwater. So you remove freshwater, that leads to a stronger AMOC, but at the same time, you keep the AMOC depth approximately constant. And he's done 3 series of those simulations here. And so now we can look, at these whole 2-dimensional phase space here of AMOC strength versus AMOC depth, and look at those separate effects. And here's the pre-industrial just for reference. Okay, so if we just look at here now, what is shown here is the correlation coefficient with the C13 data. So for correlation coefficient, we want, the better models have the higher correlation coefficients. So the orange here would indicate better models that agree better with the data than blue symbols. And what you can see is that here the dark orange numbers are in between here. So for intermediate AMOC depths of between about 2 kilometers and 2.5 kilometers. So both shallower AMOCs and deeper AMOCs have smaller correlation coefficients. But you can also see that the correlation coefficient mainly varies for AMOC depth, sensitive to AMOC depth, whereas it is not sensitive to AMOC strength, right? So all those isolines here are horizontal, essentially. And that is also true for the RMS error shown in the in this figure here. RMS error, we want lower values. So lower values are more consistent with the data, indicated in blue here. And now you can see blue all for these shallow AMOCs, but no matter what their strength, they all have similar RMS errors. But the deep AMOCs really have much larger errors that can be excluded then. So what we can say is that the C13 is really sensitive mostly to AMOC depth and not to AMOC strength. And that is also, if you look at the different basins separately, the Atlantic here, for example, or the Pacific. In the Pacific, there seems to be some, maybe not as horizontal, the isolines, but then again, I'm not so confident in the Pacific data because first of all, there's less, and then other processes may affect the Pacific rather than the AMOC. So, but for the Atlantic, the isolines here are horizontal, which indicates that that C13 cannot be used very well to reconstruct AMOC strength. Okay, and for radiocarbon, we essentially find the same thing. The correlation coefficient is not very sensitive here, but the RMS error also has more or less horizontal isolines that would favor these intermediate values here for depth, but they are not very sensitive to changes in AMOC strength. And that may be surprising because if many people think that radiocarbon is like a clock. It may include rate information, but if there's rate information in there, it is really hard to see. The depth really is dominating the radiocarbon distribution rather than the strength of the AMOC. And Juan has tried to find out why that could be the case, and one reason seems to be the reservoir ages in the Southern Ocean, and that he's plotted them here on these left-hand side panels. So that's radiocarbon reservoir ages in the Southern Ocean, which determine preformed values for much of the deep ocean. And in the lower plot, it shows those reservoir ages as a function of AMOC depth, and the upper plot shows them as a function of AMOC strength. And whereas you can see that both are correlated, but the upper panel is much less correlated than the lower. So those reservoir ages in the Southern Ocean seem to be related strongly to AMOC depth. And exactly why that is still something that we're working on that we haven't figured out completely yet. But that is a first clue on why the AMOC depth is so strongly affecting radiocarbon ages in the whole ocean. And then we can also, of course, in the model look at the different patterns that you get from AMOC depth versus AMOC strength changes on these isotope distributions, and that is shown here in this graph, which would be the last one of this presentation. In the upper, the green surrounded frame includes simulations with a strengthening of AMOC. So those two simulations have 21 and 14.5 Sverdrups, but they have a similar depth, 3.1 kilometers in each case. So they indicate the strengthening of the AMOC, and on the left is the C13 response shown, and on the right, the radiocarbon response. And as you can see, if you strengthen the AMOC, you push more North Atlantic deep water into the South Atlantic, because that is positive in C13. You have a positive anomaly in the deep South Atlantic. And then it also affects upwelling and productivity, which causes this decrease, more remineralization of light, isotopically light C13 in the upper ocean, in the Indian and Pacific Oceans. But in general, the anomalies are kind of small compared with C13 anomalies you get from a depth change, as shown in these lower, surrounded by the magenta frame. Especially in the deep North Atlantic, you get much larger amplitudes of C13 changes, more than 1 per mil, compared to the 0.2 per mil or so for the strengthening. And then similar for radiocarbon, if you increase the strength of the AMOC, the South Atlantic deep waters get younger, but only that changes only 100 years compared to much larger radiocarbon age changes if you shoal the AMOC, as shown in this lower graph here. So, perhaps we can use some of these fingerprints of lower and, deepening and strengthening to make some progress in the future. But the bottom line is that these isotopes mainly inform us about the strength, about the depth of the overturning, and not so much about the strength. And perhaps, additional proxies may benefit there, like neodymium or protactinium. And there's a similar paper that was just published here about using ESM that came to similar results. And I think I'm going to stop here and be happy to answer any questions, or I hope that I've presented Juan's results adequately. Juan, feel free to say if I've said something wrong or so.
Andreas, this is Melanie. I have a question.
Yes, hi Melanie.
That was really interesting, thank you. I guess I'm wondering, maybe this is really a question for Juan, but can you go back to the graph where you showed how with Juan's model runs you can explore the two-dimensional parameter space?
This?
I think so, yes, right. So let's see. I guess it seems like, if I'm understanding correctly, the effect that you get depends on the mechanism you use to force the change in depth of the AMOC, right? Whether you use changes in North Atlantic freshwater fluxes or Southern Hemisphere moisture diffusivity. And I guess I'm just wondering, are there other ways to force that change that might give you equally different results, or are those really the only two physically relevant options?
No, I don't think they're the only physically relevant options. You could change winds, for example, and get effects on the AMOC. You could change, as I said before, Bering Strait through flow. Although that, we know at the LGM it was closed, right? So there was no through flow. But in terms of LGM versus modern, but winds are uncertain for sure, and so yes, you could probably get different circulation strength and depth with winds, but we have not looked at that. So all we've done is these two kind of types of perturbation experiments.
Yeah, I guess what I'm really getting at is not just the process by which the AMOC depth changes in the model, but you're saying that with the way that you're looking at it right now, that you can't really use these isotopes to constrain AMOC transport. But I'm wondering if that conclusion would remain the same if you, for example, change the wind instead, like you're saying. Like, do you think that because the isotopes might be affected differently, that the conclusion could change?
Yeah. That could be. I mean, you know, if you change southern hemisphere winds, for example, we know that that also has an effect on the AMOC, but I'm not sure depth versus strength, you know, how that would affect things, but that may be something we could try.
Anyway, it's really interesting. Thank you.
Thank you.
So Andreas, back at the start, you showed that graph of the different dissipations with the different ice models of the present day. And so those dissipations seemed really, you know, really different, 1 terawatt to 3 terawatts. So what's the main thing driving that difference?
Well, it is, as you can see, the sea level lowering in itself, that is the difference between the black and the green line here. So that is only a relatively small effect. So the other changes in the bathymetry due to the different ice load and also the ice extent, that changes the geometry of the basin. That is what, you know, what gives you that much more dissipation compared with just a constant sea level lower than 120 meters. And so those changes are, you know, the regionally dependent response of the lithosphere to those ice loads. But then also the ice extent, as I kind of tried to mention here in the Southern Ocean, especially, that region has been identified by Sophie to be very important. And you can see this in the Weddell Sea here. The ice extent in this reconstruction is I-6G. That's, I think it's at the shelf break, essentially. So the ice would extend all the way to the shelf break. Whereas in the ice-5G, it is much further inland. And that, you know, that what looks like this relatively subtle change to the geometry still causes these large differences in tides and tidal energy dissipation. And one thing I should mention here is that Gary Eckbert has shown this already many years in his kind of pioneering paper on the LGM tides, is that the Atlantic is close to resonance. And when you go to the LGM state, you get even closer to resonance. So, and that is, I think, why the Atlantic is just so sensitive in terms of tides to these relatively small changes, relatively subtle changes in the geometry of the basin. That, you know, when you're getting closer to resonance, you can get much large, you can get very large changes for a small change in the boundary conditions.
Right. Okay, that makes sense. Really interesting. Thanks.
Andreas, this is Christo. Can you hear me?
Hi, Christo. Yes, I can.
Yeah. So I've been, we know from ice core reconstructions that Greenland was actually extremely cold during the last glacial. And so it cooled by probably more than 15 degrees, like 15 to 20 degrees. Well, at the same time, Antarctica did not cool all that much. And so I've been looking at many different model simulations from the LGM, mostly in the PMIP family. And it's clear that the only way you can make Greenland that cold is if you have a weak AMOC. And the only way you can get, Antarctica to cool as little as it does is by having, again, a fairly weak AMOC. And so I'm wondering if you can look outside of the ocean, maybe also for trying to figure out the difference, the influence of the depth and the strength of the AMOC. So do you think that Greenland temperature, for example, can tell us something on the depth versus the strength of the AMOC?
Well, I don't know. I would rather go to ocean interior data to find something out about the strength or depth of AMOC. But I mean, you're right. I mean, the overturning affects temperatures, and many people are using surface temperatures essentially as a proxy for AMOC. Like the more recent, the reconstruction of AMOC changes over the last millennium, for example. Ramsdorf, just uses essentially a region in the North Atlantic south of Greenland, SSTs, to reconstruct AMOC. I've always been a little bit skeptical about that because, of course, surface temperatures are affected by many things other than the AMOC, right? So, what I guess I would say is that, of course, temperatures are influenced by AMOC, but because they're also influenced by other things, you have to be careful. That, of course, that whole argumentation also applies to all the proxies that we're using here, right? That are affected not only by the AMOC, but also by other things. So perhaps by combining them, combining different proxies may be the best kind of shot that we have. Complementary proxies, what I would call them.
Yeah, that makes sense, right? Because you were showing, I think, that for the 13C, really only the depth of the AMOC matters. So you had not much of a constraint on the strength. Whereas I don't think that Greenland cares at all about how deep the AMOC is, right? It cares about heat transport. Mm-hmm. And so the combination might be really powerful.
Mm-hmm.
Okay, so we've just gone 4:30, so let's finish it off there. Thanks for speaking, Andreas, and we'll see everyone next week. We've got Aaron Pettit talking about some more ice ocean related things. Thanks, everyone.
Thanks, everybody.
Thanks, Andreas. That was great.
Thank you, Andreas.
Thank you.